In this video, we're going to go over the problems you had from section 10.4 in the Big Ideas, and we're going to look at the problems that were the more difficult for you. So the first one is number 3, and in number 3 it says, describe 2 ways to find the total number of possible outcomes of spinning this spinner and rolling that die. Well, whenever we have compound probability, or the probability of 2 or more events that are occurring, we are going to use either the fundamental counting principle or tree diagram. So I'm not going to create the tree diagram for this because I'm going to test out the fundamental counting principle first to see how many possible outcomes there are. So what that means is I'm going to take the number of possible outcomes, individual outcomes just on this spinner, which there are five outcomes, and I'm going to multiply it by the number of outcomes that are on this die. There are 6 possible outcomes. So fundamental counting principle says take the number of outcomes from this activity and multiply it by the number of outcomes for that activity. So 5 times 6 would be 30 outcomes. Well, I'm not going to draw a tree diagram. That'll take me a while. But if I did, I would also have 30 outcomes. So the 2 answers you should have chosen are to use a fundamental counting principle with a total number of 30 outcomes, and to use a tree diagram with 30 outcomes. All right, problem number 5. This one a lot of you had difficulty with. It's one of my favorite types of problems, and that's how many combinations could a combination lock possibly have? This lock, and this is just like the ones on your lockers, is numbered from 0 to 49. And then it says each combination uses 3 numbers in a right, left, right pattern, just like you guys use at school. So find the total number of possible combinations for the lock. So that means you have to have 3 numbers. You have the first number, then you have the second number, and then you have a third number. Now, if you turn your combination lock for the first time, you're going to have from 0 to 49 are the numbers that could come up. That's actually 50 possible outcomes. So you could have 50 different numbers for the first number on your combo. Now, regardless of what you put on the first number, what's available for the second number? Well, again, the second number has available from 0 to 49, so there are 50 possible outcomes that the second number could be. So the second number is 50. Then the third number, same thing. The third number could be anywhere from 0 to 49, any one of those numbers. So there's another 50 possible outcomes for that one. So then if we take 50 times 50 times 50, we're going to get 125,000 possible outcomes. This makes a lot of sense because it's going to be harder to open up a combination lock if you know there are 125,000 possible combinations. You would be there for a very long time trying to break into this lock. All right, this is a fundamental counting principle problem, and it says find the total number of possible outcomes for this situation. So this is a clown, and we're looking at the number of suit options he has. There are 1, 2, 3 suit options. Wig options, there are 1, 2. And his talent, or his or her talent, is either balloon animals, juggling, unicycle, or magic. That's 4 outcomes. So when we multiply 3 times 2 times 4, we end up with 24 possible outcomes. Okay, again, we're going to use the fundamental counting principle to find the total number of possible outcomes, and this is for a meal. So for the appetizer, you have the choice of nachos, soup, spinach dip, salad, or fruit. So that means 1, 2, 3, 4, 5 different outcomes for that. For the entree, You have choice of chicken, beef, spaghetti, or fish. So there are 4 outcomes for the entree. And then for dessert, you have a choice of cake, cookies, or ice cream. So you have 3 possible outcomes for that. So 5 times 4 times 3 is 60 possible outcomes. All right, now this is problem number 14. This one is a little tricky because there is one very important part of this question, and it says without replacing. And this was actually a preview into what we're going to be working on later on this week, which is probability where you have different outcomes from one event to the next. So in this problem, you randomly choose one of the marbles. So you have 4 marbles to start with. Without replacing the first marble, you choose a second one. Okay, so the number of marbles on your first pick that are available is 4. The number of marbles on the second pick, if you take one out and leave it out, then on the second pick, you only have 3 marbles. So for instance, if you took out the blue marble on the first try, there were 4 to pick from, and you took out the blue marble, and you leave the blue marble out, when you go back in to pick the marbles out the next time, you only have the choice of the green, the red, or the yellow. You no longer have the choice of the blue one. So that means that when we do the fundamental counting principle, we're going to do 4 times 3, which would be 12. So the answer to the second part of the question would be to find the total number of possible outcomes, and that would be 12, not 16. Now, the 2 ways, part A, that you can find the total number of possible outcomes, the same ways we've been doing. You're going to either use a tree diagram or the fundamental counting principle. All right, in the remaining problems, they're all using this spinner and flipping a coin. So what I did is I created a tree diagram with the outcomes of spinning the spinner and then flipping a coin. So we have 10 possible outcomes, and if you did the counting principle, you would have 5 possible outcomes on the spinner, and then for heads and tails on a coin, there are 2 outcomes, so that would be 10 total outcomes. So all of our probabilities are going to be based on 10 possible outcomes. So now in this one, we are looking for the probability of spinning a 1 and flipping a head. So spinning a 1 and flipping a head. So when I go to look how many outcomes do I have a 1 on the spinner and a head, I'm looking at this outcome, and that's just 1. So there's 1 possible outcome out of 10. And I can't simplify this probability or this fraction, so it's going to stay 1 out of 10 outcomes. Okay, using the same spinner and flipping a coin, now we're looking for the probability of spinning an even number and flipping heads. So if I look at my outcomes, my even numbers would be when I spin a 2 or a 4. And then the second part of that is we're looking for flipping a head. So spinning a 2 and a head happens once, and a 4 and a head is another one. So that's 2 possible outcomes out of our 10. 2 possible outcomes out of the 10. And I know some of you put in 2 out of 10 and it marked it wrong because I think it wanted you to simplify it to 1 out of 5 possible outcomes. Okay, same events happening. You're going to spin the spinner and flip a coin. We have the same tree diagram, same outcomes. This time we want to know the probability of spinning a number less than 3 and flipping tails. So a number less than 3 would mean you're going to spin, or you're looking for a 1 or 2 on the spinner and tails. So if I look at my outcomes, I'm looking for a 1 or 2 on the spinner, and I'm looking for tails to happen. So 1 or 2 on the spinner and tail happening. That is 2 possible outcomes out of 10, which again would reduce to 1/5. Okay, same thing, spinner and flipping a coin. This time we're looking for the probability of spinning a 6 and flipping tails. Well, is there even a 6 on the spinner? There is no 6 on this spinner. We have no outcomes that have a 6, so the probability of you spinning a 6 on this spinner is going to be 0. So that was the answer to that problem. All right, new question. Same spinner and coin. This time you're looking for the probability of not spinning a 5 and flipping heads. So probability of not 5 means that you're looking for the spinner landing on a 1, a 2, a 3, or a 4, and one of those numbers plus heads. So that means 1, 2, 3, 4, and heads on each of those. So 1 in heads, 2 in heads, 3 in heads, and 4 in heads. Those would all be possible outcomes. That's 4 out of 10 possible outcomes. And if you simplify that, that would be 2 out of 5. Okay, this one's a fun one. Again, same spinner, heads and tails. Probability of spinning a prime number and not flipping heads. So if you don't remember prime numbers are only numbers that are divisible by 1 and itself. And in the spinner, the prime numbers are 2, 3, and 5. Those are all prime. 1 is not prime because it does not fit the definition of prime numbers. And there's an activity called the sieve of Eratosthenes that if you picked 1 as a factor of all numbers, then we would not have any prime numbers. So 1 does not work. So we're looking now for all the outcomes that are prime and not heads, which means we're looking for 2, 3, or 5 to come out on the spinner and tails. So the ones that are 2, 3, and 5 on the spinner and tails, we've got 1, 2, 3 possible outcomes out of a total of 10. And we can't simplify that, so we're going to leave the answer as 3 out of 10 outcomes.